the nth roots of unity. So we're looking at this specific situation where z to the power of n is equal to 1, or negative 1, but the real numbers whose modulus are 1. When you plot all the solutions, not just for these ones, it's for anything when it's z to the power of n could equal any number, but you'll get a regular polygon when you plot them if you were to join them all up. Let's look at the fifth roots of unity. So z to the power of 5 is equal to 1. We can now use derivatives to come up with solutions for that. 1's a real number, so I'm playing with the conjugates there. I'm going plus or minus 1, plus or minus 2, but remember all you need is, in this case, 5 consecutive numbers. So I'll get cis 0, 2 pi and 5, minus 2 pi and 5, 4 pi and 5, minus 4 pi and 5. Now let's plot those. There's our first one, cis 0, which is of course just 1. Cis 2 pi and 5, and its conjugate. Cis 4 pi and 5, and its conjugate. And if I was to join them up, there we go, we get our pentagon, and it lies on the unit circle. Now we play with these roots of unity. Omega is a complex root of z to the power of 5 minus 1 equals 0. Show that omega squared, cubed, power of 4, and power of 5 are the other roots, because we know there's going to be 5 all up. When they say complex root, they're actually meaning non-real. I mean, even though 1 is a complex number, they're talking about the non-real ones. So if you see them say a complex root. Okay, we know z to the power of 5 is equal to 1. We also know omega is a solution, because they told us that. Therefore, omega to the power of 5 must equal 1. Now if I play around with that, omega to the power of 5 to the power of 5 would be 1 to the power of 5, which is also 1. Well, therefore, omega to the power of 5 must be a solution. Omega squared to the power of 5 would be the same as omega to the power of 5 squared. Oh, but omega to the power of 5 is equal to 1, so that's 1 squared, which is 1. So omega squared is a solution. Omega cubed to the power of 5 would equal omega to the power of 5 cubed. Omega to the power of 5 we know is 1. 1 cubed is 1. Omega cubed is a solution. And then we do it with the power of 4 as well. And so yes, they are all solutions, they are all roots. In fact, omega to the power of anything would be a solution. Yeah, that's sort of a bit cumbersome doing it for each individual one. And that's only when it was power of 5. Imagine if we're looking at something like, oh, I don't know, z to the power of 20 is equal to 1. Do you want to do that 20 times? I mean, a lot of work. We could simply do it like this. Z to the power of 5 is equal to 1. That's what we've been told, so we know omega is a solution. Well, if k is an integer, then omega to the power of k to the power of 5 would be omega to the power of 5 to the power of k, which would be 1 to the power of k, which is 1. And so therefore omega to the power, well the ones we're interested in, squared, cubed, power of 4, power of 5 are also roots, but as I say, actually to the power of anything would be a solution. This question here is quite common. Prove that 1 plus omega squared plus omega cubed plus omega to the 4 is equal to 0, and there's a few different ways we could do it. Here's the first one. Well, we know that these 5 things are the roots of the equation. That's what we just showed. So I could play with the sum of the roots, minus b on a. If I go back to that equation, well the coefficient for b was 0. There was no term there for, well this one z to the power of 4. Therefore that sum must be 0. I could do it that way. Oh, by the way, how did omega to the power of 5 all of a sudden magically change to 1? So I should make a note about that. Oh, well, we know omega to the power of 5 is equal to 1, because that's what we said. I could start with the equation itself and factorise it. Remember, we said omega to the power of n minus 1, if I factorise that, it's always going to have a factor of omega minus 1, and then in the second one, basically the powers of omega go down by 1, and so we'll get omega to the power of n minus 1, n minus 2, and so on and so on and so on, down to omega to the power of 0, which is 1. Well, solutions to this equation, there is only going to be one, and it's that the second parenthesis is equal to 0, because we know the first one can't equal 0, because we specified that omega was the complex root, so omega can't equal 1. Well, therefore it's not possible for omega minus 1 to equal 0. Therefore it must be the other factor that's equal to 0. Or another way we could do it, well, we're trying to find this sum. Well, that's actually a geometric pattern. First term is 1, common ratio is omega, number of terms is 5. So if I use my formula, a outside of r to the power of n minus 1 over r minus 1, I get this, but of course look what's on the top. There's a factor there of omega to the power of 5 minus 1, which we have said is equal to 0. Therefore the whole thing's 0. There are different ways you could go and show, or prove in this case, that particular result. Alright, we're now going to create a quadratic equation whose roots are omega plus omega to the power of 4 and omega squared plus omega cubed. Sum of the roots would be this, but hang on, we just said 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0, therefore this must equal -1. Product of the roots. If I expand that out, I get this. But I can tidy that up because we know omega to the power of 5 is equal to 1. So I could write that as omega cubed plus omega to the power of 4 plus omega squared, which again is equal to -1. I can now create a quadratic. That would be x squared minus the sum of the roots, so minus 1 is plus x, plus the product of the roots, -1. There's the equation that we're looking for. This time it's going to be a complex cube root of unity. So solution to omega cubed is equal to 1. Use the fact, so I don't have to prove it this time, they've given me the result. Use the fact that 1 plus omega squared is equal to 0 to evaluate this. Now, when you're playing with these roots of unity questions, basically there's just two things you know. In this case it's a cube root of unity, so I know omega cubed is equal to 1. But the other thing I know is the one that they've told me there, that 1 plus omega squared is equal to 0. Using those two things, I should be able to manipulate any question they give me. So 1 plus omega squared, I could rewrite as minus omega. But minus omega cubed would be minus omega cubed, and omega cubed we know is equal to 1. So using those two facts, I come up with the result of -1. Fraction here. Algebraic fractions pull together a common denominator, but I'll tell you what, it's a lot easier to play with a denominator with one term than it is two terms. That 1 plus omega I can rewrite as minus omega squared, and the 1 plus omega squared I can rewrite as omega. And then that is a much easier fraction to play with. I'll just get -1 minus omega over omega squared, but -1 minus omega must be equal to omega squared, and I get 1 as the answer. This time I'm going to form a cubic equation. The roots are going to be 1, 1 plus omega, and 1 plus omega squared. I will get z minus 1. I know that's a factor because they told me there was a root of 1. That means the other factor, because I'm forming a cubic, must be a quadratic. So I'll have z squared minus the sum of the roots. Add those together, I'll get 2 plus omega squared. Plus the product of the roots. When I multiply those two together, I get 1 plus omega squared plus omega cubed. Now let's play with those. Okay. Well, omega plus omega squared I know is -1. And 2 minus 1 would just give me 1. So I've got z squared minus z. Now if I look at the constant term there, 1 plus omega squared plus omega cubed, but hang on, 1 plus omega squared, that's equal to 0, and omega cubed, that's equal to 1. I just end up with 1. There's the equation factorised, so let's expand it out, and we end up with this, z cubed minus 2z squared plus 2z minus 1 equals 0. So when we're playing around with these roots of unity, really it's just two facts you're playing with. Omega to the power of n is equal to 1, and then the 1 plus omega squared plus omega cubed up to omega to the n minus 1, whatever that happens to be, is equal to 0. We're going to solve this equation. Well, it has that pattern. See, I know z to the power of 6 minus 1 would be that factorised. It'd be the same thing, but with z minus 1 out the front. And I can find the solutions to z to the power of 6 minus 1 equals 0. I know it would be, well, this is 2 pi k on 6, where k is, and I just need 6 consecutive numbers there. But this is the one I want to solve. And it's very similar, but not quite the same. But I can make it look the same. Let's multiply by z minus 1, but to balance it out I've got to divide by z minus 1 as well. Well, that means I effectively now have the top of the fraction is z to the power of 6 minus 1. And when I'm solving a fraction equaling 0, it's the top of the fraction that equals 0. So effectively I'm solving z to the power of 6 minus 1 equals 0, but I don't want the solution of z equals 1, because I can't have that on the bottom of the fraction. That's the factor that I've introduced into this problem. Okay, well that means the solution that I'm looking for, or solutions, would be all of these 6 roots of unity, but just not including z equals 1. So it must be all these. This is pi on 3, minus pi on 3, 2 pi on 3, minus 2 pi on 3, and pi, all of those are nice exact values, so I can actually work those ones out. So there they are in x plus iy form, or Cartesian form. Quite an old HSC. They told us that omega was this specific thing, cos of 2 pi on 9 plus I sine 2 pi on 9. We have to show that that to the power of k will be a solution to z to the power of 9 minus 1 is equal to 0. Well, z to the power of 9 equals 1, so I just need 9 consecutive numbers. In this case, I didn't write the plus or minuses. Main reason I didn't is because I want to do this. Using de Moivre's, I can say, well, hang on, that would be the same as cis 2 pi on 9 to the power of k. And cis 2 pi on 9, that's what they told me omega was. So actually that's omega to the power of k, where k is an integer. Prove this, which essentially is that 1 plus omega, etc., etc., etc. It's just that the 1's been moved to the other side. So I'll do it. Which way did I choose out of all the methods? I just went the sum of the roots way. So I know the sum of all our roots will be 0. So if I move the 1 over to the other side, I get the result that they want. Hence go and show this result, the cos of pi on 9 times the cos of 2 pi on 9 times the cos of 4 pi on 9 is equal to 1/8. Z to the power of 9 minus 1 would factorise like so, because we know all the factors. Now you might look at the order I put them in and think that's a bit weird. You know, logically, wouldn't you just go up by powers? But look very closely at what I've done. Z minus 1, there was that one. But then look at the next one in pairs. And what do you notice about the powers? Power of 1, power of 8, adds up to 9. Power of 2, power of 7, adds up to 9. Power of 3, power of 6, adds up to 9. Power of 4, power of 5, adds up to 9. What's the significance of that? Because they will be the conjugates. If the two powers add up to be the n, they're going to be the conjugates. Therefore, when I expand these two, the power of 1 and the power of 8 out, I'll get the quadratic z squared minus the sum of the roots, but because they're conjugates, the sum of the roots will be 2 cos, and for this one, well, it's going to be 2 pi on 9. The next pair, it would have been cis 2 pi on 9 to the power of 2, so the angle became 4 pi on 9 using de Moivre's. The next one would have been the cis of 3 pi on 9 to the power of 2, so it would have become 6 pi on 9, and then the last one would have become 8 pi on 9. Plus the product of the roots, well, the beautiful thing about roots of unity, then the conjugates will multiply together to give 1. Tidying that up a little bit, because one of those I know the exact value of. The cos of 6 pi on 9 is the same as 2 pi on 3. Cos of 2 pi on 3 is negative a half. Negative 2 times negative a half means that factor is just z squared plus z plus 1. The other ones I can't work out. But I don't need to, because my question hasn't actually asked that. It's asked what's the product of these three things. Okay, well, how do I get it? Here. Look at the individual factor. I would like to end up with just that single cosine term. In other words, I got to get rid of this z squared. How can I get rid of z squared? Oh, I've also got to get rid of the 1. Hey, let's make z squared equal to negative 1. In other words, let's make z equal I. So if I substitute z equal I into that whole thing, on the left hand side then I now have I to the power of 9 minus 1. Right hand side, I minus 1. But now the second factor is just minus 2 cos 2 pi on 9 times I. And then the next one, minus 2 cos 4 pi on 9 times I. The next one will be I squared plus I plus 1, which is I. And the last one, minus 2 cos 8 pi on 9 times I. Now, let's play around with this. Okay, first thing I'm going to do, I'm going to pull out all those i's. So there's an I in the second, third, fourth and fifth factor there. Pull them out, then I've pulled out I to the power of 4. All right, we're getting closer. I'm also going to pull out the 2's. That'll bring me 8 out the front. I've got negative I to the power of 4. Well, that's equal to negative 1. I've got this I minus 1, which will cancel with the I minus 1 on the left-hand side. Take the negative out. I've now got negative 1 on the left-hand side. Getting very close now. But see, I now have to sort out the 8 pi on 9 because the question didn't have 8 pi on 9, it had pi on 9. 8 pi on 9 is obtuse, so the cos of 8 pi on 9 would be the same as minus the cos of pi on 9, the acute angle. Now those negatives cancel, divide by 8, and I've shown the result that they want. Cos pi on 9, cos 2 pi on 9, cos 4 pi on 9 is equal to 1/8. Let's have a look at one from a couple of years ago now. It was the fifth roots of unity, but this time it was equal to negative 1. Okay. Z is a complex number. Oh, thank you for that. Solve the equation, and I'm giving you a really big hint here, by finding the 5 roots of negative 1. Oh, that's how you do it. All right. Now it'll be pi plus 2 pi k on 5, and 5 consecutive numbers. I'm drawing out the conjugates by going plus or minus 1, plus or minus 2 there. There are my 5 solutions. Okay. Show that if Z is a solution, doesn't matter which one, if it's one of those solutions, except for the negative 1 solution, then U that equals Z plus 1 on Z is a solution of U squared minus U minus 1 equals 0. All right. If I want to show something as a solution, I'll substitute it in. So let's substitute in the Z plus 1 on Z into U squared minus U minus 1. Expand out. Now, what have I done there? Hang on. All of a sudden I've got rid of my fractions. Remember, we're playing with roots of unity. So Z to the power of 5 is equal to 1. So if I multiply the 1 on Z squared plus Z to the 5, all I'm doing is multiplying by 1. I can turn that into Z cubed. And the 1 on Z, if I multiply that by Z to the power of 5, again I'm just multiplying by 1, but it becomes Z to the power of 4. But notice the sign change, because in this one, Z to the power of 5 was equal to negative 1, not positive 1. So in those fractions, you'll notice the sign has changed. It was plus, became minus, and so on. Let's make it look like what we see normally when we're writing polynomials. So Z to the power of 4 minus Z cubed plus Z squared minus Z plus 1. We've got to show that's equal to 0, because we want to show this a solution. If I multiply top and bottom by Z plus 1, which I can do, Z doesn't equal negative 1, so I'm not putting 0 on the bottom of the fraction, that's fine. But then the top becomes Z to the power of 5 plus 1, and Z is a solution of Z to the power of 5 plus 1 equals 0, therefore that equals 0. So what we now know is that U equals Z plus 1 on Z would be a solution of U squared minus U minus 1 equals 0. Hence, go and find the exact value of cos 3 pi on 5. Well, I'll let Z equal cos 3 pi on 5 plus I sine 3 pi on 5, which was one of those fifth roots of unity. Z plus 1 on Z. Again, when I'm playing with roots of unity, the reciprocal is indeed the conjugate. So Z plus 1 on Z will be twice the real part. 2 cos 3 pi on 5. Now, we also did something else. We had this equation, U squared minus U minus 1 is equal to 0, which I can find solutions of. It's 1 plus or minus root 5 on 2. But But what we saw is this. Z, the Z I picked, is a solution to Z to the power of 5 plus 1 equals 0. I deliberately picked that. And if it is a solution, then Z plus 1 on Z is a solution to this quadratic. Therefore, 2 cos 3 pi on 5 must be one of these. It's either 1 plus root 5 on 2 or 1 minus root 5 on 2. The question becomes which one. But I know 3 pi on 5 is obtuse, therefore it must give me a negative number. So it's not going to be 1 plus the square root of 5. It's got to be 1 minus the square root of 5 on 2. So I now know 2 times the cosine of 3 pi on 5 is that. Therefore, the cosine of 3 pi on 5 is equal to 1 minus root 5 on 4. Okay. So 3C, playing with our roots of unity.